All right, so you guys, we're going to be finishing up the Unit 4, which is really all about DMM use and circuit testing, but this time specifically it'll be on parallel and series parallel. And pretty quickly you'll see the most important thing is being able to test a series circuit, because like I've said several times, when we have a problem in a parallel circuit, we basically determine which part of the circuit it's in, and then we test it as a series circuit. And same with the series parallel. So we'll go over it because these circuits, they do functionally different. They have a different formula, for example, for calculating amps. They have some different theories as to, like, you know, when we talk about series, if you want to add light bulbs, that's great. You add bulbs, that adds resistance. But on a parallel, if you add bulbs, you actually reduce resistance, which means you increase the amperage, which means you'll blow the fuse or, you know, cause damage and whatnot. So just got to make sure you understand the application of that Ohm's law correctly, more so than how to do the Ohm's law, by the way. So here you go. If we were to look at this series circuit, let's evaluate a few things, or this parallel circuit. Can you tell why this is parallel? Like, especially if I were to back up and look at a series, right? Here's a series. You have a voltage, resistor, a resistor, and a resistor in line, right? So you have three loads there. Right here, you have, in this case, actually, four: resistor, 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 but they're not in line. Can you tell the difference? Like, they have their own path. So if we're to look at this like a road, there's one road, and then the road splits off into four different roads or lanes. You got one lane, and then it goes into four lanes, right? So that's what makes this a parallel. So I joked last time about Christmas lights. Old school Christmas lights, all the lights were in series. And so if you had one bulb fail, all the lights were out, and you'd have to determine which one it was, because if it's in series, like back here, if this resistor number one, R1, fails, that's going to mean there's no electrons able to flow anywhere in the circuit. Make sense? Whereas in a parallel, if R1 fails, R1 will not have any current flow, but the path with R2, R3, and R4 will remain just fine. They'll be the same. And so it's a little different, but I feel like visually it makes some sense. What's also interesting is if you look at the A, right, the A being like your amp meter, right? So if you were to try to measure amperage, what's really different if we back up to series is on this series circuit, can anybody remember what A1, A2, A3, A4 would be? Well, let's make it with the switch closed. Your amperage reading should be the same. Measuring amperage in a series circuit is really simple because it's the same everywhere, right? If you only have one lane, it doesn't really matter where you measure the number of cars because all the cars have to go through that one lane. Make sense? So you can measure amperage at anywhere, and it's all the same. Whereas when we jump over to parallel, the amperage at 5 is different than the amperage at 1, amperage at 2, amperage at 3, amperage at 4. They're totally different. So to determine amperage on this, it's actually a much more complicated formula. The good news for you, assuming you're not an electrical engineer, who cares about the formula? Nobody wants us to calculate Ohm's law. I've still never yet had a customer come through the service drive and say, hello, I would like you to calculate Ohm's law in my electrical system today and show your math and give me the numbers. What they may say is, hi, my tail light doesn't work. And if it's one tail light, your brain should process it in one way. But if the customer says, hi, my tail lights do not work, none of them, then you should be processing it in a different way. Understanding how the Ohm's law works is great, and that's what we're going to focus on. But calculating it, not so much, although we will calculate it just to prove that's how electricity works because it's science and stuff. All right, so if we were to look at this, what I can tell you just looking at this circuit, first off, let's trace it. Red comes off of here, goes through the switch because it's closed, right? Goes here. And remember, A5 is not a load, it's not a resistance, it's just the amp meter. Come over here, goes here, goes here, goes here, goes here, right? So it splits 4 different ways and hits all 4 of those resistors, at which point it should basically switch over to being ground. Go to ground, and this one ties right in, and this one goes to ground, and this one goes to ground, right? So if you were to visualize this as like cars, and then keep in mind the chassis ground is here. If you were to visualize this as cars, for example, the cars leave this point, all of the cars are sharing this part of the road. Would you agree? All the cars are on that road. Then some of the cars will go over to resistor 1. Some of the cars will go to resistor 2. Some of the cars will go to resistor 3. Some of the cars will go to resistor 4. And they all will drop the appropriate voltage at this point. So first lesson would be the sum of all the individual resistors, the sum of all the electrons that flow through the individual paths with the individual resistors will equal the total, right? So A5 right there, that's like how many cars are going on the main road. And if you think about it, if they all came through the main road, the freeway or something, and then some got off at exit 1, some got off at exit 2, some got off at exit 3, some got off at exit 4, but they all came from the freeway. At one point, they were all traveling on the freeway together. Then they split off, and they don't necessarily split off equally. It would depend on the amount of resistance. So if you look, resistor 1 is 2, resistor 2 is 4, resistor 3 is 2, resistor 4 is 1. So you'd kind of be like, huh. Well, that's going to mean that if you had, let's just say 10 amps, different amounts of amps are going to go on different amounts of circuits, and the less resistance there is, the more cars are going to go that way, right? So in that way, it's a little more similar to water, right? Less of a resistance means it's sort of like the resistor is opened up, the valve is opened up a little bit more. If you have a valve that's opened up more water is going to go through the 1 ohm, and a lot less water is going to go through the 4 ohm, right? But how much? Like, I don't know. Well, we got to calculate that, and we can calculate it. The other thing to consider is, you notice I traced red all the way to the resistor on each of the 4. So if I've traced it red, what do you think the voltage should be available right here? It's a full source, right? So 12. What about on resistor 2? 12. What about on resistor 3? 12, and resistor 4, 12. So when I talk about the parents hand down the $12 and the siblings had to share it, yeah, that was true for series. But in parallel, it's kind of more like each sibling gets a credit card, a debit card to the parent's bank account. They all have access to the full amount of money, right? So in that way, it's kind of different. So you have each of these resistors that have direct access to the full source voltage. So the cool thing is, if you wire in a bulb like this, it's not going to get more and more dim as you keep adding bulbs. It's going to be at full brightness because they all have full access to the source voltage. See how that's just a little bit different, right? So that's one way to look at it. The other thing is, you got to notice that on the resistor, this resistor is going to drop the full voltage, because if you were to just break it off and look at a section, if 12 volts makes it to the resistor, and then after the resistor it goes straight to ground, we know it's going to drop the full 12 volts. So it's going to be a very predictable voltage drop. Cool. The voltage is going to be basically of the same amount of voltage is available to all these. if you were to cut a wire, let's just say I make my cutter right here. If I were to cut a wire right here, what would happen? All the bulbs would go out? No, because look, we blocked off one lane, but see, we still have access to these 3 lanes, right? So it's just very different. Cool. Now here's what's crazy. If this resistor didn't work, do I think the problem's up here? If the problem was up here, what would happen? Bingo. So the second the car rolls in, we are determining, is this like something that's happening on the main highway, or is this something that's more happening on one of the particular exits? Make sense? So if we got an issue with one bulb, I really only care about it starting from here, going down to, in fact, technically, I really only care about it. If it was here, that would take out 2. So it'd actually be like, no, I really only care about it right here. It could be anywhere in this, but then it would have to end here. So that's kind of what I meant when I said, like, if you have a problem with a series circuit, you're just going to determine what part of the series circuit it is. And then if I'm between this blue line and this blue line, I misspoke. If I have a problem on a parallel circuit, all I need to really do is determine which part of the parallel circuit it is and then diagnose it as a series. If I'm between this blue line and this blue line, all this is irrelevant. All this is irrelevant. If you actually look at it, all I have is a little series circuit right here. So I just diagnose it as a series circuit anyway. I just don't want you diagnosing over here and over here and over here because none of those spots are relevant. Okay, kind of makes sense. So far, parallel should not be real intimidating. Like, as an example, this would be a simple one. Let's say customer rolls in, and I'm going to draw this switch closed so we make sure we get the concept correct. So let's make this switch the brake light switch. Fair enough? If you want to test the customer's brake lights, what are you going to do? Somebody's got to step on the brakes, right, to start. So when I step on the brakes, I close the switch. So let's just diagnose this with the switch closed, because that's pretty normal. If I have no brake lights at all, neither one of these are lighting, where do you think the problem's going to be? It could technically be up here. It couldn't be here. It couldn't be here. 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 So I'm not going to test those. Well, I can't say couldn't be, because think about this. Is it possible that they actually have 2 blown bulbs? Is it possible? Potentially, yes. Is it likely? No. But people are kind of crazy. Sometimes they're like, oh yeah, my first tail light was blown for 2 years, then the second one blew, and now I'm thinking about fixing it. You know, so it's possible, or the brake light or whatever. But generally, we're going to start with, like, remember, we're accountable to time. So if you want to bill time for money, you don't want to spend too much excessive time testing things that are not likely, right? You could be like, oh, well, I need to test those bulbs because it's possible. But it's like, it's not likely. So why don't we start with what's likely? Make sense? So if it were me and I had both bulbs off, I agree. It could be up here, but also couldn't it be right here from this point down? Could potentially be the ground if they share a ground. What if I were to redraw this, however, and have them both have their own individual ground? Then I'd be like, no, I don't think it's got 2 bad grounds. I would definitely say it's probably on the positive, right? Just logically thinking through how the system works. So if we were to have, let's say, a blown fuse, what would the effect be? True, it'd be open. So what would the customer notice, though? No brake lights. So, like, that's possible. I think we should check that soon. I don't know that I would spend a lot of time checking one bulb. I think I'd probably go first for the fuse, right? So generally when this happens, I start to make a plan for how I want to approach this. So if it was a brake light switch, that would take out both of them too. I agree. What if the customer came in and they said, my left brake light isn't up, but my right one works? Do you think I should check the fuse? I won't even pay you to check the fuse. That's just straight up, you don't know what you're doing. Do you think I should check the switch? No. Thank you. I won't even pay you to check the switch because that's not how it works, right? So once in a while, if somebody has car problems and I say, yeah, send me the technician's diagnosis story, they're like, okay. And then I can pretty quickly follow it. And if they say customer states one brake light was out, I tested the fuse, I tested the switch, I'm like, all right, either one of two things. This technician really doesn't know electricity well because those are unnecessary tests. Or the other thing I got is maybe they do know, but maybe they're trying to milk it a little bit. You think that's possible? They'd be like, they probably didn't even do those tests, but they're just trying to write the story longer because they want to get paid, good diagnosis time, which is part of the reason people will have a big issue with, like, the common standard here is if you have a problem and it needs diagnosis, you agree to 1 hour diagnosis. The reason that, I'm going to say we, but like I wasn't there in that beginning, but I started automotive a long time ago where that was pretty common, and a lot of new people are kind of like, why do we do it that way? Why don't we just charge the customer exactly what it takes us? Well, I'll tell you. If the car comes in for one tail light out or one brake light out, we got to be able to price them something up front. You can't be like, well, we need to diagnose it. And they're going to say, how much is that? You're going to say, like, I don't know. It could be like 1,000,000 hours or like 11 minutes. Like, we don't know. You got to sign it over to us and not have a price. That's not really good. The other thing is we want to incentivize you all to know how to diagnose quickly by having more knowledge and a better understanding of the knowledge, be able to apply it better, right? So it would be kind of counterproductive if we said, well, we're just going to pay you however long it takes you to diagnose it. Most problems we're able to diagnose in an hour or less. Some problems definitely not. More than transparent on that fact. But if a car comes in and they've agreed to 1 hour diagnosis, and it'd be kind of excessive for it to be a brake light bulb. But let's just say it's a brake light enough, but they've already put a new bulb in it. They may actually really have to sign for an hour diag. At that point, it'd be counterproductive for me to say, oh yeah, I need to test this wire, I need to test this fuse, I need to test this switch, I need to test this. This is a splice, I need to test over here, I need to test this ground, I need to test this. Then it'd be like, you're going to spend how much time to diagnose a problem? Whereas if they've already signed for an hour diag, you know what I'm going to say? I'm not worried about it being up here because this one works. I'm not worried about it being down here because this one works. I'm going to test maybe right here to right here, and most likely I will figure it out in under 1 hour. So if I think about this, if I have it diagnosed in 30 minutes, but the customer agreed to an hour, the flat rate technician gets paid the hour, how much money did I make? Depends on my hourly rate, right? So give me a number. What do you want to pay this example technician per hour? Well, just the technician, not the whole dealership, not the shop. So the shop may be billing 100 something an hour. Some of them are 200. Some of the other ones, I know of dealers right now today, $250 an hour. However, that's not what the technician's making.
30 to 50.
Yeah, so let's just say, let's go with, we could pull California labor laws into this. California labor law says skilled labor is double minimum wage required. To me, that makes some people feel really warm and fuzzy, but like to me, honestly, nothing's really changed. The free market would determine a good technician's worth at least double minimum anyway. Now we get up, so we'll roll on those laws. If you're skilled labor, how do you define that? Generally, it would mean you have specific training or licensing. So like if you work we pick on McDonald's, let's pick on something new. You want to have it your way? You want to do Burger King? Or what you want? In-N-Out's a good job. You could work at In-N-Out. I don't exactly know what In-N-Out people make right now, but truly, if you decided you went to In-N-Out and you're like, you know what, I'm not going to do your doubles anymore. I've had enough. I want a union. I want double my pay, and I want all these things. You know what they're probably going to do? They're going to be like, move out, and we're going to get somebody else. And in 7 days, you are replaced. as a minimum wage type of general worker. Does that make sense? You can't replace a technician in 7 days. You probably can't replace a technician in under a year, or maybe 2, or maybe 3, right? So as soon as it's skilled labor, it's mostly defined by that. Like if it's skilled labor, it takes a lot of time, training, licensing, maybe apprenticeship, maybe a certain number of hours. So a lot of trades, you have to work with a mentor, electrician for 2,000 or 3,000 hours, which would be like a full-time year, by the way. If you work 40 hours a week for a year, and let's say you take a week of vacation, that's 2,040 hours. I know the numbers in the top of my head. So if you want somebody who has 2,000 hours on the job training, that's a year. You can't replace them in a week. Cool? So double minimum wage applies. The other thing is tools. If you have your own tools and you're basically like an independent, you show up with your own tools and you do your job, you're double minimum. Minimum wage is what, $16.50 right now? So double minimum is $33. So a true technician is going to be starting at $33 an hour. Cool, we'll go off of that number just because that'd be the minimum. If you worked on the car and you got paid by the hour, you made $33, right? Let's not talk about tax, but you know about that. So you didn't bring it home no $33 an hour, but you earned $33 an hour. Let's say that the customer signed for the hour diag. You figured it out in 30 minutes. You still only made $33 an hour. But what did you do for that other half an hour? Hopefully you did another one, right? So if you understand this system, you want to work smarter, not harder, but you also want to work harder, so that's not really accurate. If you work smart and you figure it out in 30 minutes, that's not your time to do this, right? That's your time to be like, give me another one, right? So if you do it right, you'd knock out an hour diagnosis in 30 minutes, you take your 33, and then you go knock out another hour diagnosis in 30 minutes and you take 2. What's your hourly? How much are you making per hour if you're doing that?
66.
Bingo. Now that's how you're making $66 an hour, right? So with that being said, you just got to understand the way my brain works, and the way that I want yours to work is not so that you can figure it out quickly to go chill. Chill's a word that's really popular right now that I would probably delete from your vocabulary if you can help it, unless you're content with where you're at. But if you're trying to improve, I would not be chilling. Chilling is like at best maybe treading water or maintaining. If you're trying to come up, you don't be chilling, okay? So if you get what I'm saying, you're like, hey, I don't need to do all these measurements. I want you to do the minimal measurements possible and the most diagnosis in your mind by understanding it. Get what I'm saying? So that way you can knock out 2 diagnosis jobs and you can make $66 an hour or similar. And that's really how technicians make good money. They can make good money by the hour, but like the technicians who are really, really making money, it's because they're really smart and they can diagnose quickly and they can repair quickly. And it's not to say you can cut corners and just be like, I'm not going to measure any of this stuff. I'm just going to shotgun parts in there and be like, oh, it's the switch. It's got to be the switch. It's like you can do a few measurements and diagnosis. All right, so if it was both bulbs, go ahead. I'll take your question.
About the salary situation.
Okay.
So when they first go in and they get that job as a technician,
Yeah. They don't start there, though, so you know. It'd be like you get started as a lube tech and you bust out tons of oil changes. And the oil changes, you don't really learn that much. It's very that's just straight by the hour. Yeah. So if anybody gets hired, it may be $16.50 to do oil changes, and you'll be like, forget that. I don't want to do oil changes for $16.50 when I can make 20 at In-N-Out. I'm going to go to In-N-Out. It's better. Maybe, but at In-N-Out, unless you become the manager, you're screwed. I mean, you're disadvantaged economically, I should say. Right? So for me, my advice would be take the lower paying job that has a better opportunity for you, right? So I take the stupid oil change job, but I go to a place where I could be an oil change technician, but also with an agreement that, hey, I'm in school, I'm studying, I'm pursuing ASEs, I'm pursuing my understanding. If we're slow, can I work under a mentor technician and become an apprentice? That's the ticket right there. Not the money. The money's going to suck, especially when you're working under a technician some of the time, because the shops want your hours to be billable, right? So if you're doing oil changes, they're billing the customer. If you're working under a mentor technician, you're not producing anything that they can sell, right? So it's a losing business plan. It's a big benefit for you, and it could be a benefit for them if they do it right and if you're somewhat loyal. If they train you up in-house and then you become the really good technician and you stay, it's better to train your own technician who understands your culture and who's somewhat loyal and then becomes a major producer of income, for your business. But a lot of times what happens is people get a little bit of training and then they go bail on that job for 50 cents down the road. They get a 50-cent raise and then they're like, forget it, we're not going to train anybody anymore. So, I'm very invested in that. But if you work your way up and you pass your things and you get maybe your manufacturer credit or your ASE or your whatever, and you prove to them you can do it, then yes, then you become a technician. What's your question after that? Yeah, so I'd love to say that, hey, if you guys study this class, you'll just go roll in as a technician, but it just, we don't have the hours for that. Typically a tradesperson is developed over 2 or 4 or 5,000 hours. That's like 1 or 2 to 2.5 years. For me, I was an apprentice 2.5 years. I can't get you to be a technician in like one class or all the classes. You can get the whole certificate and the degree, but you need to go get the experience, which takes thousands of hours, much longer than this program is. Like if you were to do every class in this program, it's around typically about 1,200 if you do every class. And then I'm saying most trades people are developed in 2,000 to 4,000. So you got to go work too.
I guess I do have one.
Shoot it.
Okay, so let's say you do go in there at a dealership, maybe you start off at $16 an hour.
Yeah.
And you're a new tech for, I don't know, maybe 6 months. I don't
Sure.
know.
No, that's a good goal. Yeah.
Then you go to another spot, or
Yeah.
you build it.
Start to move up a little. Yeah. Uh-huh.
So do you start making more money after you get certified through taking a test, or can you start?
Depends. All for negotiation. But the way I'd sum it up that I think will make the most sense is like if we'll focus it on this problem. If this car came in with brake lights are in-op, a customer has a problem right now. The brake lights are in-op. They need the problem solved, right? So why are they in the shop in the first place? They came to the shop so that you could provide them a solution, right? So if they came in with brake lights in-op and you said, oh, you need a brake light switch, we're going to charge them for that, right? So the second that you can be put on a job and provide solutions to people, you're worth money. When you're hired initially, most of the time you can drain the oil, you can put the drain plug in, hopefully put the drain plug back in, hopefully torque it, hopefully not have it fall out. That's not really worth a lot of money. Make sense? So the second that you can start solving problems like this, they can start putting you to work and billing more, right? So the customers aren't willing to pay much for an oil change. They think it's a rip-off at $50. $50 is totally not profitable. I wouldn't even run a business to try to make $50 on an oil change. It's a loser every time. But if I could run a business doing diagnosis and I could say, hey, you need to pay an hour to diagnose this problem, and the hourly rate's $100 an hour, and I could hire one of you for $33, we're talking about $76 of leftover profit for every hour. That's enough to probably have an insurance company and a business and some licensing and some things. So truly my answer is the second you can deal with problems like this quickly, effectively, accurately, not have comebacks, you're worth being promoted. How that looks on a case-to-case basis is going to totally vary, but that's the truth. The truth of the matter is if they won't move you up because you don't have the license or the test or whatever, those are factors, right? Like if you're for a manufacturer, you have to have that for the manufacturer to pay the warranty claim. But if you're working for an independent, there's no state regulation or federal regulation saying you have to have your certification test. So the second that they can roll you out and have you effectively providing solutions to customers in exchange for money, I'd say let the free market do its thing. It's a double-edged sword. They can fire you or they can pay you whatever they want, and that hurts. But the second that you're worth it, somebody else will pay you. So like you don't have to beg for it. Just be like, hey, I can fix problems like this. You're going to have to like, I need to be promoted or otherwise I got a job offer down the road. The toolbox has the wheels. You push the toolbox down the road or whatever, and then they'll pay you. Like, so you got to understand how you function in the free market, right? So that's always where I'm coming from when I explain these. It's not just the technical. It's more of the how do we apply the technical in a way that can get you paid better, in a way that can get you promoted, in a way that can get you more dollars per hour worked, etc. Cool? So if you kind of understood this, you can do most of the diagnosis on this circuit just understanding it, which means you understanding it and studying it and knowing it is worth money, correct? So I'm trying to sell you on, if you get this, it's worth money. So let's say we jump and we apply a little bit more and we do some figuring. So like if you look right here, we got 4 ohms and we've got 6 ohms. Exactly what the total amperage would be on this circuit, I don't really know. We'd have to do the formula, and I'm going to show you the formula. But part of the reason I'm not great at the formula, truthfully, is just what I said. I understand the free market. I try to maximize dollars per hour for myself, but also for you or anybody else. I could be bilingual, like I can talk with the minimum wage person, but I could also talk with management as high up as it goes. So immediate manager, service director, general manager, dealer principal, whatever. I can relate to kind of everybody, right? So my main takeaway on this would be if the car came in, I don't really care what the total amperage is. I don't really care what the individual amperage is. I don't really care about any of that unless I need to have that information to offer a solution, okay? So now thoroughly understanding that, I'm going to tell you, I'm not even really worried about this 4 ohms and 6 ohms. But what I do want to point out is, you notice right here, we started with 12 volts coming up, going through, let's assume the switch is closed. 12 volt splits, 12 volts goes to each of these. If we just had if we just had this side, it would be much easier to diagnose how many amps. But again, like who cares, really? We don't usually do the calculations. We're just trying to diagnose why the customer's lights are in op or why one light's in op or whatever. The thing is, when we added a whole nother lane and we added this, see, we had 6 ohms and then we added 4. So is the total 10? Question, 10 ohms, question mark? And the answer is no, because we didn't just add resistance. We did add a resistor, but we also added another lane. So if we add a whole nother lane, do you think that's going to make more cars flow or less cars? Are the cars going to be more choked out or are they going to be more free to drive? We added a whole nother lane, right? So what's really weird about a parallel is every time you add another resistor, assuming you also add another lane, this would actually reduce the overall resistance. So the overall resistance is how we calculate the number of amps, right? So we could know the voltage, and if we can calculate the amount of total resistance, we can determine the amps. Cool, I'll show you the formula, even though you'll never use it. But what I need to make sure you understand is if you keep adding bulbs on bulbs on bulbs, you're adding resistors, but you're actually decreasing the resistance because you keep adding lanes to the freeway additionally. Cool? So if you're in the garage and you're like, hey, I want to add a light bar to my Jeep and I want to add this and I want to add that light, I want to add that light, great. You're adding resistors, but you're also adding additional lanes and additional wiring because they're in parallel. Every lane you add, that's going to increase the amps through this wire. Cool? So if I keep adding lanes, do you think eventually I might exceed the rating of that fuse? Right? If it was a 10 and I keep adding lanes on lanes and lanes, and then I end up to the point where it's flowing 11 amps, what's going to happen to the fuse? Poof, it's going to blow. Yeah, exactly. So should I add a bigger fuse? Thank you for remembering. typically the fuse is set to protect the wire. So maybe this wire is rated for 11 amp. Let's say 12 amps. If the wire is rated for 12 amps, we're going to probably protect it with a 10 amp fuse. If we start to flow more than 10 amps, like let's say we flow 11 amps, is there an 11 amp fuse? I've never seen an 11 amp fuse. So what do? We throw in a 15. We pull the red out and we throw in a blue, a 15. If you throw in a 15 amp fuse, which is weaker, the wire that can handle 12 or the fuse that can handle 15? Ooh. So now you start to overheat the wire. That's when it catches on fire. Okay, so make sure everybody understands this is parallel in application. You can't keep adding lanes. You should really talk with the developers of communities and be like, hey, you can't keep adding lanes and lanes and lanes of roads with houses on them, and the same freeway still has 2 lanes. You understand? You're overloading the freeway. It's the same concept. For some reason, they don't understand it. Or maybe they do, because every house they build, you know, they get to collect more property tax, so they're all about it, right? But this wire right here has a limit, and it's all designed. So we will apply the math. A 4 ohm and a 6 ohm, we could calculate what the total resistance is, and we will, but I'm just going to do one slide on it. So if we were to look at this is it traced. I think it's pretty simple. The total current in the circuit equals the sum of current in each branch. All right, so let's just say we had, what size are they? This is 4 and this is 6. So the 4 ohm would flow a little bit more amps. Let's say this one over here was flowing 8 amps and the 6 was flowing a little bit less. And let's make that one 4 amps. If you have 8 amps here and 4 amps here, what do you think I have on the main road? 12, exactly. So if you have 8 cars here and 4 cars here, that means 12 cars came down this main road, right? That's the visual, that's the application of the Ohm's law in amps in a parallel. See how that's so different than series? Series was the same everywhere, it's only one lane. Once it's multiple lanes, you got different amounts of amps flowing on different points of the circuit, but all the individuals would total to become the main road, right? That's the total amperage is equivalent to all the individuals. Cool, that's kind of the point. Now if we were to look at voltage, and truthfully, when the car comes in, I'm not even calculating amps. That's one thing I can't highlight enough is we're going to talk about how to calculate it so that way you know how to calculate it, because that's my job in this class. But like really, you're not going to calculate amps when the car comes in. I would just go right for voltage, and I could diagnose the car, and I could make a recommendation, and I can wrap up my diagnosis in 30 minutes, and I can get another piece of crap car in here and diagnose that piece of junk, garbage car, horrible car, in 30 minutes, which is some of the reasons why I call them all junk, because I just don't get emotionally attached. Like I just move them in, diagnose it. Kind of like the doctor doesn't get really emotional when they give a diagnosis. It's just like, keep your mind clear. Don't make it personal. Don't try to make it the cheapest thing so that you can, you know, give them good news. Like whatever it is, it is. Make sense? So car rolls in. I'm just going to say, like, let me diagnose this relatively quickly. Here's what I would predict. We start with 12. 12 volts should go across the fuse. We might drop a tenth, hopefully less. It might go across the switch. We might drop a tenth, hopefully less. It splits off. We get 11.7 to the bulb and 11.7 to the bulb. I would probably start right there. I'd probably crack a cover off of this trunk and I'd go right to the brake light bulb and be like, what you got available? Boom. 11.7 on this bulb, 11.7 on this bulb. That tells me everything I need to know about the positive side of the circuit. Then I do the same thing. Let me check for ground on the bottom side. I should have good ground. That tells me everything I need to know on the ground side of the circuit. Now, if they had 2 bulbs in op and I had 12 volts here and 12 volts here, and I had ground here, 0 volts here, and 0 volts here, those 2 bulbs are blown. However, unlikely, it's a matter of fact, and they could do it in 4 measurements. Make sense? What was your question?
That means when you're
Yeah.
So you're just going to be doing volts then?
Yeah.
You're not going to be doing amp. When would you use amperage or ohms in a practical sense?
Fair question. Let's say this car came in with a blown fuse. First off, there's a couple different ways we could approach that. But if your 10 amp fuse is blown, that means it's flowing more than 10 amps. But how many amps? I don't know. So maybe we would measure it and be like, how many amps are you flowing? But truthfully, that'd be pretty rare, because normally when a fuse blows, it's probably because like this is shorted to ground. So I'm not even sure that I'd calculate the amperage right off the bat. What I'd probably truly do is like I showed you in the very end of the last one, how we could, it was a little tough to take in all that, but how we would diagnose a short to ground. I'd put a bulb across the fuse, and if the bulb lights, that means it's getting 12 volts here, and that means it's getting ground here. And I would just disconnect various points until the bulb went out, at which point I know I took the ground away. I'd just be like, oh, your short to ground is between here and here. I need to inspect further, and I find that Sparky's radio shop sent a screw through the harness and it's grounded or something, So I don't even really do a whole calculation. But if you understand electricity has there's laws, it follows laws, the numbers don't lie. It can't like be different on this car. It helps keep us all in line so that we all understand like your numbers tell the story. So you can't be like, well, I got this measurement, but on this car it was different because the electricity wasn't feeling good that day. So we do cover the laws, but the main voltage, available voltage or voltage drop tells you everything you need to know, like 99% of the time. Then let's just say I was totally tripped out. Let's just say I just diagnosed it as 2 bad bulbs. Is it possible? Yes. Is it likely? No. So maybe because I'm just like, am I right on this? I'm a little freaked out. Maybe I switch my meter to ohms and I check the ohms across the bulb. How many ohms do you think I should have on each of these bulbs? Like I could even back up. We had some numbers. Exactly. And if I measure OL and OL, didn't I just kind of double check myself that like, yeah, these bulbs are definitely bad. So once in a while, I'll throw resistance in just to double check myself. Some of the more practical times you might measure resistance is like maybe with an engine coolant temperature sensor, or like there are times, but typically with electricity, the voltage drop and the available voltage combined, it's going to tell you everything. You could even calculate the ohms using the voltage and using the amperage anyway. So like the voltage just tells you a lot. Cool. So the other way you could do this is you could voltage drop, right? I described available. We had 12, we had 11.8, we had 11.7, 11.7, and we had 0.1. But we could also voltage drop it with the T-Rex arms, remember? We could have the red lead before the load. So I could have the green lead down here, and I could have the red lead up here. And at that point, all we're doing is testing between the red and the green. So what are we voltage dropping? Just the fuse. A fuse should drop like nothing, like a 0.1 or maybe less. And I could voltage drop the switch, which should drop a 0.1. And I should voltage drop the load of the circuit, which should drop basically everything, or almost, minus whatever little pennies we lost. Make sense? So you could available voltage this, or you could voltage drop it. It's the same concept, but the thing is, bringing it back to what we talked about, you don't want to just measure a bunch of crap because you're not worth, it doesn't make sense to spend more time than you need to. You get what I'm saying? If you spend the minimal amount of time and you get it correctly diagnosed, that's the winner in the free market, evil capitalist empire, right? So like if you just roll up to the car and you spend all day poking, how is that fair? You're going to just bill the customer 8 hours to be like, yeah, I voltage dropped everything in your car. And they're like, why? All I wanted was my brake lights to work. So then on the other side of the coin, someone would say like, well, I'm not going to measure anything. I'm just going to slam whatever part in there. And if it fixes it, cool, right? So on one hand, you milking the diag hurts the customer. On the other hand, you not doing any diag at all and throwing the wrong parts at the car hurts the customer. So I want you to find a spot where you can prove that that's what's wrong by your measurements as quickly as possible, as least invasive as possible, without messing stuff up and without being wrong. That's when you're at your peak value, to be really honest. And trust me, if it's a well-run company, the manager is going to understand if you can work on more cars, you can make more money. But if you can work on more cars and you can make more money, you're going to make them even more money. Make sense? If you're getting the $33 an hour, but their labor rate's $100, they're getting, what's that number, $67 an hour on every hour that you make. If you're turning out 12 or 16 hours a day, you're collecting 33 on that. They're collecting 67 on that. So like your productivity is beneficial to all. And even for the customer too, if you think about it, like you could go to the customer and say, hey, I need to charge you however long it takes and like kind of check a bunch of unnecessary stuff. Or you can give them a flat fee and be like 1 hour diagnosis, I will diagnose it. Sometimes you go a little over and you don't bill them extra. If it's a complicated diagnosis, you may be like, hey, I've done all these diagnoses, but I need more time. You should have a clear, path of what you've done and what it's eliminated. Honestly, on this diagram, you can't spend more than an hour diagnosing this. There's something wrong. Cool, but sometimes the problems are kind of crazy. And it'd be a much more complex one. And you might be like, hey, I spent an hour, I need more time. You should be able to say like, here's what I measured and here's what I can tell you is not the problem. But I'm still trying to determine, I got to check individual things. Is it this harness? Is it this fuse? Is it this switch? Is it this wire? Is it this splice? Is it this bulb, that ground? That's not that much stuff. But on some components and systems, there's like a lot of stuff. So you might not have it all figured out in 1 hour. You can go for more time, but it's kind of better if you can figure it out quickly and still get the hour. Everybody wins. Go ahead, Tracy.
Let's say that situation that you circled earlier.
Sure.
The area.
Uh-huh.
And do you repair it first and you write something down?
Generally, no. If you diagnose it, essentially all the customers agreed to is the diagnosis, right? So it's kind of similar to the doctor. You roll in the doctor, you're like, oh, I got a tummy ache. They're going to probably come in and be like, hey, we did some tests, we did some checks. Or let's just say, better yet, it's a broken bone. They're going to do some tests, probably an x-ray, right? You're going to have to pay for that. And then they're going to come in and be like, hey, we saw it. Here's the break. Let's look at the picture. Here's my measurements. Here's my readings on my DMM. That'd be us, right? But similar. Here are your options. But first, all they really signed for on the estimate was the diagnosis. So if we go to them with a diagnosis and we say you need this thing, or you need that thing, or you need the other thing, we need to rework the estimate and be like, you're covered for the diag. This is what you paid. Here's the result of your diag. Now this is what you need to repair it separately. We don't just jump on and start fixing stuff and whatever. Like if you really do it right, the customer should always know exactly what's happening. The customer should never be upset because you explain this is the cost to diagnose it. And if they say like, oh, all you did is plug in your fancy tool, you'd be like, no, I don't. Look, I had to access these connectors and check for these voltage readings and study the diagram. Like we get paid for that. That's legit. But it needs to be correct though. You can't be like, oh, it's the bulb, but then put a bulb in it, didn't fix it, and then be like, oh, never mind, it was actually the fuse, because you charge for diagnosis time to make sure you had the right thing that was the problem. Make sense? So it's pretty good. Then they'll approve the repair or they'll decline the repair. And oftentimes, to be honest with you, they decline the repair because they know somebody else who can fix it cheaper, and they probably do. But why didn't that person diagnose it? Well, that's because the diagnosis skill level is much higher than the wire repair skill level. The diagnosing the circuit is much more demanding, requires much more knowledge, much more study time, much more certification, much more experience than the person who puts the new bulb in there, right? So like, it's not totally unheard of for them to come in and have you do the diagnosis, take your diagnosis money, and then they leave to have somebody else do it. But whatever, that's our role sometimes. That's partially why I've seen a number of dealers, if they think that the person's sketchy, they won't charge 1 hour diag, they'll charge 3. And they'll be like, hey, the diagnosis is $500, take it or leave it. And they're like, oh, never mind. That if they weren't willing to pay that they probably didn't really want it fixed. They just wanted to use you for the diagnosis, which is why we don't do that for free. It'd be like telling the doctor, do you do free x-rays and diagnose the broken bone? It'd be like, no, why should we? And you'd be like, well, yeah, that's how the shops do it. They do the diagnosis for free. Like, I doubt it. The doctor at that point would have no incentive to do a good job. They'd just be like, yeah, we need to do surgery. We make a lot of money on surgery. You know what I'm saying? So not a good idea. All right. Sure. Shoot it. Your questions are good.
Let's say it's just that wire.
Yeah.
In the bulb, right?
Sure. Let's say it's, I'll mark it up.
On the wire, or do you just put a new wire there?
Good question. We're going to cover that in a little more detail. I'm going to teach you guys wire repair, but also depending on the nature of the failure, the extent of the damage, depending on who's paying for it, depending on if the car's warranty, all that type of stuff. Sometimes we do a whole harness. So for me, I favor wire repair because it's more cost effective, but I'm also very, 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 very picky on how I repair wires. And you'll see, I would trust my wire repair just as much as a new harness, whereas some other people, they're not that good at wire repair, sometimes hard to access, so it depends. It's up to some extent, it's up to us. So for me, I'm going to offer what I think is the most appropriate, whereas if the car is under warranty, they may or may not approve it because it's up to the manufacturer. Sometimes the manufacturer may say, no, we don't do wire repair. We do whole harnesses. Put a $3,000 harness in it. We do that sometimes, like kind of a lot of the time. Cool. And then here was that application you asked about the voltage. We check voltage mostly. In fact, let me delete that. If we check voltage mostly, I agree. Here's when we could check continuity. Like we could measure the continuity of that bulb. And honestly, if you wanted to start with ohms, you could check the bulbs with ohms. It's just, remember, like I was saying many times, checking resistance isn't as accurate as checking voltage, so I would go with the voltage. Cool, it's a dynamic test. Alrighty. So I think for the most part, I think you guys understand, if we had one bulb out, we're worried about something like here to here. If we have both bulbs out, I'm probably more worried about up there or even potentially down here. So you'll know pretty much like what part of the circuit to break it down to and then test that part of the circuit. Cool? And that's why I kept saying, if it's a parallel problem, you're probably just going to determine which part of the circuit you're going to diagnose and then diagnose it as a series. Most of those series skills from last time are what you really need. Cool? All right, so if we were to look at this, let's do some predictions. Can anyone predict, right? I won't even trace this. We're just going to pull some numbers. Can anyone predict what the voltage available at point E should be where I just pointed? 12-ish? Yeah, let's just go with a source. Yeah, something like that, but 11.9 and 12.0, it's the same number, and effectively. And if it's a car that's got a charged battery, maybe it's 12.6, and if it's a car that's running, maybe it's 13.8 or whatever, but source voltage there. What about on F? I don't think so. And that was my test. So if it was a series they share, in a parallel, they both get 12, and they should both drop the full 12. So there should be a 0 and a 0. Even though there's 2, it doesn't work the same as series, right? Series is sharing. Parallel, it gets its own access, and it should drop the full voltage across the load. All right, very good. Let's go with, I think I have a couple more. Voltage available at point, whatever, this point. Still 12. Now there's 3 resistors, 3 loads, so what should this be? 0, it doesn't matter how many loads there are, they all drop 12 volts. They should, okay, makes sense. Now this next one's a little confusing. That's okay, it's a good thing. You can do some of these experiments, by the way. Ooh, look at what happened here. So right here, I'll even help you with this one, I will trace. 12 volts comes through, 12 volts, 12 volts, 12 volts, right? then we should look on the ground side. Ground goes to the switch. In fact, I'm going to totally trip you out. Right now the switch is open, right? What do you think I should have available at this point? We got a disagreement between 12 and 0. I'd like to highlight a key point. Switch is open. That would mean what should happen, not with the switch open, what happens is the 12 volts will go through the load and all the way down to the point of the open, okay? So that's kind of like the drawbridge is up, right? The cars go around, they go, I'm ready, I'm ready, I'm ready, and they wait at the point of the open. That's just what they do. Then, of course, we'd have ground right here. Cool, and that'd be true for all these. You will have 12 volts going all the way to the point of the open. That's just a matter of fact. All right, but let me redraw this and close the switch. We just closed the drawbridge. What happens here, well, I guess I shouldn't tell you. What do you think I should have at this point? At the green point right here. Now I should have 0, right? Cool, because now when I close that drawbridge, these electrons are like, we're out of here, it's closed, I'm gone. Okay, cool. This is, normally, honestly, this is how we test the circuit. But sometimes just to understand, if you have an open ground, the voltage will go all the way to the open point. So if you have voltage on the ground side, it's because the ground is open. It's just the way it is. All right, now, what about at this point? Should be 0. What about at this point?
You'll have some voltage.
Yeah, exactly. Because if you look at it, now we're worried about this part of the circuit all the way down to this part of the circuit where they rejoin. And if you notice, this is actually series, right? It's got to go through this one and then through this one. So these are going to share. So let's just say this one was 6 ohms and this one was 6 ohms. What should I have here? 6. Oh, I'm not even writing that number. Never mind. We're not doing that. Let's say this one has 4 ohms and this one has 4 ohms. Then I agree. This one would have 6. There we go. So because this resistance is the same as this resistance, they're going to split it because they're arranged in a series, right? So the series laws still change. You could have a bit of a series circuit inside of a parallel circuit, but that doesn't make it a series parallel, FYI. What I would like to point out why this is so valuable is, let's just say this resistor was more of like an unwanted corrosion. Remember how corrosion in the circuit becomes resistance? You'd have a bright bulb, right? 1, 2, 3. A bright bulb, 1, 2, 3. And then with this one, you'd have a dim bulb, 1, 1.5. You'd have a dim bulb. Why would you have a dim bulb? Yeah, it's got too much resistance in this part of the circuit. This resistor has no effect on this, has no effect on this. It only affects this part of the circuit, and that's why we diagnose it as like a little mini series circuit. Cool? So there's 2 ways to think about it. One, the added resistance will lower the amps, so the amps went down, which makes it not glow brightly. Or the way that I think about it, because we usually think from the perspective of voltage, is this one's only consuming 6 volts because, unfortunately, this secret, unplanned child is getting half of the allowance money when I was supposed to get the whole 12, but I got to share it with this. Remember, like, that's kind of the joke. There's an unwanted resistor right there that's going to consume a proportional amount of voltage to the resistance. Cool? So this circuit was a little trickier, but hopefully you found it fun. And that's essentially how we would diagnose a series circuit, even a parallel circuit, even if it had a little mini series part in it. Cool? So if the bulb is dim, it may have unwanted resistance, but it would only have unwanted resistance in the part of the circuit that would affect that particular bulb, right? If this bulb is dim, we're not worried about high resistance on the fuse. What if we had high resistance on the fuse? Which bulbs would be affected? All the bulbs. Exactly. So the sooner you can be like, I could diagnose quickly because I know how electricity works, the more you're worth and the money. That's kind of why I'm here, in case you didn't know. Trying to help you get there. All right, so with voltage, I think you'll find this pretty simple. So I don't think we'll have to spend a ton of time on it because it's kind of repetitive, right? If we were to do this voltage measurement right here, we got the red, we got the green. So we're measuring voltage across the source. What do you expect across the source? About 12-ish, right? So if we start with a 12, then I were to go over here, this is not available voltage now. This is a voltage drop. If I were to take my green lead and put it on all these points, and my red lead, and let's just say we start with the first one, how much voltage drop should I have across the first load? 12 volts. How much should I drop across the second load? It's still 12 volts, right? So it's just like what we just talked about, except we're looking at it through voltage drop, not just available voltage. They should all drop 12. All of them should be dropping 12. That's how the parallel works. Good. And then if we wanted to do some math, we'll highlight a few things. We agreed V1, V2, and V3 should be 12, 12, and 12. 12, 12, 12, and even V4 we agreed should be 12. So you're correct. You nailed that. That was good. Then if you wanted to determine the amps on the individual circuits, here's how you do that. And you're going to notice this is repetitive, so we won't spend a ton of time on it. You remember this diagram, right? V, A, R. If we look at, let's just say, resistor number 1 is 12 ohms. We measured the source voltage as 12 volts. So this would be 12. This would be 12. That becomes 12. Change over to my pen. Divided by 12, which equals what? 1. 1 amp. Cool? That's how you diagnose that one, 1 amp. Now, if you are getting pretty sharp with math, if this has 6 ohms, how many amps should be flowing there? That has 1. If it's got 6 ohms, it's going to be 12 divided by 6, which equals what? 2. Correct? What if you had 2 ohms? It'd be 12 divided by 2. How much is that? That's 6 amps. This is the way that I would actually troubleshoot this. The book gets a little more engineering. So this material is made by a really smart guy. I know who he is, but it's I like to do it. I like to keep it simple, stupid. You know the KISS method? I'm keep it simple, stupid. So if I have 1 amp, 2 amps, and 6 amps, what do I have up here? Just knowing how it works and not loving math that much. 6 plus 2 is 8, 9. So this is going to have 9 amps. And I figured that out just by doing the series part individually and understanding if there's 1 car, 2 car, and 6 cars, apparently when they were back here, there was 9, right? Just knowing how it works. That's how I process this. There's different ways to do it, okay? And I will show you another way to do the total amperage, but again, like I said, it's like, if it was something that was going to help me maximize my earnings, I will go study all this math tonight. But nobody cares. And nobody's going to pay me more. And, you know, that's kind of how my mind works. Right? So we proved that we could do that math. It wasn't that hard. Cool. So let's say we want to measure the amps. This is just a summary of a series, right? It's 12 volts, 4 ohms. So we'd plug it in with the VAR, 12 divided by 4, and we come up with 3 amps, right? We've done that one. How it can be done right here is, like we said, we would take the, we would go ahead, we could do the VAR. And we would do the 12 is here. If the R is 2, that would be a 6. If the R is 4, that would be a 3. So again, what would the A3 amperage be, the total? 6 plus 3 would be a 9. Cool. So not a real big deal. That's how I would think about it, right? This is how you can show, this is how you can do it if you want to do it more as like a thorough equation. I would rather do like 2 small equations and then understand the third. Otherwise, you could do the total resistance is 1 over R1 plus 1 over R2. And that's like, you know, whatever electrical engineers can do that if they want. Okay, makes sense? If you want to do it like that, you can. Personally, I would just do this one plus this one equals this one. A1 plus A2 equals A3, whatever. Do it whichever way. Yeah?
There's just 2 resistors. It's R1 plus R2 over R1 plus R2. It's easier.
And there's so many different fun ways, all of which I hate. But that's true. The one that I found a little bit easier, so I pulled this one. This is literally copy-pasted from Google-powered AI, just because. I was like, you know what, just pull me another number. So if you wanted to find the total resistance, and see, that's kind of the problem, is back here, you know, if you wanted to find total resistance, it gets a little bit weird. If you did want to find that, not amperage, but resistance. Resistance total is 1 over resistance total equals 1 over resistor number 1 plus 1 over resistor number 2 plus 1 over resistor number 3. So resistor number 1 is 2. That would be 1/2 plus resistor number 4 is 4. So it'd be 1 over 4. That's a quarter. So it's like a half plus a quarter. And then you'd have to get rid of the 1 over, and then you could get your actual resistance. So whatever. It's another way to do it. There's several different ways. There's also calculators. Like, I don't mean the ones where you push the numbers, but you can go on Google and just do parallel circuit calculator, and you could just type in the numbers and it'll do the math for you. Boom. So truly, if you get to that point, I'm not the correct teacher for you. I'm just really not. Like, engineering is interesting to me, but it's like, if any of you really want to be an engineer, I believe that you could. 100% I believe that. But you're not going to be an engineer and also a technician to your full potential. You got to pick one. For me, I'm like, engineering, nah, I'm out. A lot of people may say, you know, the engineers, it's like a step up from a technician, but I could give you actual literal names right now of people I know with engineering degrees and that are professional engineers, and the jobs kind of got a little sketchy, especially with AI and quite a few companies leaving California, and there's new ones every day and stuff. I know like a handful of professional engineers that are technicians in dealerships today right now. So figure out which one you want to do. If it's technician, that's pretty much where I spend all my time. That's where my mind is at. If it's engineer, I'm going to be like, you sure you want to do this? And if you do, I can't get you there. I'm out. I'm tapped out. No, I as an engineer, tech, no. And that's kind of more what I'm saying. The technician, the best perspective you can have is the technician exists to serve the customer needs. And the customer need is, my car does this thing, or my car doesn't do this thing, or my car doesn't work, or whatever. And the best thing we can do is find the most efficient, accurate, quick, practical way to get the job done. That's what the customer wants. So if you start a new automotive business and you're like, try my automotive business, we're not only technicians, we're engineers, and you decide to like show them the math and the calculations, and like, you're not going to work on as many cars. So how are you going to make a profit? You're either going to charge each customer more so that you can show them all your findings and your experimental peer-reviewed things and publish articles, and the customer's going to be like, you know, honestly, I don't care. I just want my car to work and I don't really want to spend any money, but I'm willing to spend as little as possible to get it to work. So we conform to that. They come in, the car's messed up. If you're a good technician, you actually diagnose it. Technically, I think the customer would be thrilled if you diagnose nothing and you just happen to be a good guesser. They'd be thrilled with that. But where they're not thrilled is you guess wrong, and you tell them, hey, I told you it needed this thing, and we charged you $500, and it didn't fix it. And now you got to pay more. And sometimes it's not 500, sometimes it's thousands. So like kind of recently-ish, I had a friend of a friend, like a distant friend. If you don't have friends right now, just work on cars and you'll have lots of kind of friends, sort of ish, who are friendly when their car's broken. And then when their car's fixed, not so much. So a friend of a friend, nice people actually, said, hey, my Subaru's got a check engine light, it's shaking, and it doesn't seem to shift. And I'm like, oh, okay, that sounds like, you know, maybe like it's got a misfire, maybe it's got a transmission issue, maybe it's got both, but yeah, I don't have time to diagnose that, I'm sorry. So they took it to the dealer, and I said, how many miles? And it was like 100 and change thousand miles, but it's only like 3 years old. So they took it to the Subaru dealer, a local one, and the Subaru dealer's like, oh yeah, this much diag, they paid it, it needs an engine. And I was thinking, like, it's a Subaru with like 100K, like that sounds kind of, well, I guess that could be the case, but that sounds a little bit weird. So kind of like, let me see the technician notes. They sent me the basic technician recommendation was, you know, needs an engine. I was sort of like, no, I want to see like what the technician actually did. So I had to go to the dealer and say, hey, can I, you know, I don't have any authority, but if I'm trying to give my friends good advice, I need to have some more information. So can I look at the technician notes? And it was basically like compression test results. Boom, I got you. Like if I see those numbers, I can interpret so much. So I look at the numbers and it was like, first cylinder was like 150, second cylinder was like 140, third cylinder was like 130, fourth cylinder was like 120, and the minimum spec was like 135. So the last two cylinders failed. And so they're like, yeah, the cylinders are low on compression. I was like, 120. Then I looked at it, it was kind of interesting. It started good and it got worse. I interpreted that whole entire test to be they didn't have the battery charger on the car when they did the compression test. By the time they got to cylinder 3 and 4, the battery was low. It wasn't cranking it that fast. I'm totally convinced that's a misdiagnosis. They quoted $15,000 for a new engine and a new this and a new that and a new the other thing. And these people, you know what they said? We can't put 15 grand into this. Like, we're just going to junk this car. And then their dad, who's actually a little bit more of a closer friend, most of my friends are like 60 something for whatever reason, was like, hey, can you check out my son's thing? Like, this sounds weird. It's a car that's 3 years old that needs $15,000 worth of work. And I was like, no, Tom, that doesn't sound right. That's kind of why I got involved. So the thing is, the technician wasn't exactly understanding what the purpose of the tests were, right? So that misdiagnosis alone, it was a misdiagnosis, okay? That misdiagnosis alone was $15,000 wrong, you understand? So like some things are small, but that one's a big one, you know? So like for me, I kind of oversaw it, and I talked with the foreman, and the foreman actually ended up being a former student. I was like, hey, like, talk to me over here real quietly, because I'm not trying to put the tech on blast, but like, dude, you see these numbers? This needs an engine because it's got 120 PSI in cylinder 4 on what sounds to be like a dead battery. Like, I'm not even sure that would cause a misfire, you know? So we had a little private conversation. What they ended up doing was passing it up the chain, and Subaru covered like the majority of the repair, and they were able to make it work, right? So the best thing all of us can do is just give an accurate diagnosis and then let the customer decide. Should they fix it? Should they trade it in? Should they get a new car? Should they take a personal loan? Should they ask a family member for help, right? But all those things, to be the right decision, all need to be because of a good diagnosis. If you give a bad diagnosis, we're really setting people up for failure. So that one got a little ugly. Luckily, Subaru covered like the bulk of it. And I kind of told them, like, let them cover as much as they can. And then, you know, I'm not sure I would keep that car. Subarus are fine. They're good cars, but like, I don't know, if they don't have a very good service department and they can't correctly diagnose, like, I wouldn't have that type of car. Honestly, the type of car I would buy either needs no service, but they all need service, or is going to offer a high, you got to have somebody who can do a good job at diagnosing to keep it going. Or you buy something brand new so it doesn't need anything. It was ugly.
It's a really scary story.
It's true.
Would you, something like that, if you're, like, if I'm a technician,
Yeah.
for instance, and it's that high of a mountain, wouldn't I want to go see someone else first and talk to
I agree, and some of that was just not, some of that was like, it was kind of a rookie tech that was like just doing the book. The book says if the compression's under 135, it's bad, so if we don't have these conversations and you don't like get a little perspective, you're just like, well, the book failed it, like I'm good. But then it'd be like, well, hey, the book also says put a battery charger on it when you do the compression testing. You didn't do that, right? So I don't think this tech was trying to rip the customer off. The engine's not even really a good job to sell. Like, that's not even like it's a profitable job in a way, but it's a hard job. So I just think that this is a person who needs more experience, which I come extensively being honest with you. I could teach you all the Ohm's law and the numbers and stuff. I don't know that it's my role to really teach you stuff like that. Like, hey, this is a big deal. If it seems weird and you're about to bankrupt a family with 3 kids, go ask somebody with a lot of experience and be like, hey, does this sound right? Because I'm about to sell an engine that's like 15 grand. And they'd be like, let me see your numbers. And be like, whoa, wait a minute. Did you have a battery charger on this? And be like, no. I'd be like, go back there and redo the test. They need mentoring, which is why I'm telling you, you got to get the experience, or you're not really going to be like a good, well-rounded tech. Cool? But, it's a work in progress, okay? It really is. So,
Did they get fired for that?
no. No, they're okay. But honestly, the reason that one's a good story was because Subaru stepped up big time and covered like the vast majority of that repair. And then when they got the car back, everything was good. But they also had to put some other stuff on there that they didn't initially sell. So they got a new engine. I think it ended up with a new transmission too. And Subaru covered that entirely. So it was like that was perfect because nobody was harmed. I mean, in a way, actually, Subaru corporate paid the bill, but I don't feel so much for them. You see their share, their earnings reports quarterly. And it's like, oh, whatever. Like, you guys. But truthfully, in that way, the manufacturer should get really serious and be like, that was an expensive mistake. How can we help technicians be better, be more qualified, be whatever? But instead, they're just like, I don't know, move on. So cool. If they don't care, I don't care. Truthfully. But I do care about you individually, so I'll try to help from my side of the equation. But if the big manufacturers aren't willing to invest more in techs, I'm going to try to do it my way. And someday they'll maybe figure it out. Maybe not. All right, so when we talk about this, we can calculate the resistance or we can measure it, right? So measuring, this you do need to do. Calculating, not so much. So how could we measure the amps on the resistor 1 part of the circuit? We'd have to open the circuit up, we agree. So we'd open the circuit right here. We'd go with probably grab red, and we're going to send the red into our meter, open it up, and we're going to go green out of our meter and go down. And the electrons are still flowing exactly where they were. That's how you correctly measure R1. Now, if you were to do R2, same thing, right? You'd go with break it open and send it to the meter, and break it open, send it to the meter. What about if you wanted to measure up here on the main highway? You do the same procedure, but depending on where you place it, you're going to measure different things. So if you measured it right here, that was just from here to here. Whereas if you measured it here, that was just from here to here. If you wanted to measure the amps right here, that's only testing here to here, right? If you want to measure the total, you don't do it down here. Technically, you could do it here, actually, anywhere from here to here. Or you do it somewhere between here and here. Get what I'm saying? So you'd break this circuit open, send it into your meter, and then send your black lead out to the circuit just where it came from. That's how you would measure each individual leg of the circuit. Cool. But
So you're saying you measured before it branches out?
yeah, exactly. Figure, you can make it visual. If you're trying to do a survey on how many cars flow on the road, if you want to know how many flow on exit 1, you got to put a device on exit 1. If you want to know how many flow on exit 2, you got to put an exit 2. If you want to know how many flow on the main highway, you got to go put a device out on the main highway. Or technically, you could put 3 devices on exit 1, exit 2, exit 3, and that would tell you how much was on the highway, assuming they all had to get off on the highway, right? So, you know, there's a little bit different ways, like different ways to measure it. It's mostly for a concept. Again, we're not usually doing a whole lot of diagnosis through amperage, unless it's blowing a fuse, in which case I do it differently anyway. And then here's the longhand math, which luckily for you we won't do. Giving you, calculating the total resistance. If you calculate the total resistance, you can calculate the total amperage, and then you can calculate the individual amperage through each circuit, right? And that's really what this is all about. Cool. So, I don't know. Short of the math, I don't think that series is that complicated, right? It's really just applied slightly different and then breaking it into, parallel is not that different. It's applied a little different, and then if we do have a problem, we just break it into a series and diagnose the part that we're worried about. Cool, that was the summary of what I wanted to do. If you wanted to do the longer math, you can. But look, we got a new type here. This, I didn't think you could see this. I need to actually hide this piece of junk. Hide. Series parallel circuits. Oh, a little different and a little the same. So let's first be practical, right? Because I already staged you on, you're not impressing the customers enough to charge them more money by being able to do the math. Ultimately, the customer just wants the stupid car diagnosed so they can spend their stupid money and get the stupid car back on the stupid road, and they're not even really happy about giving you the money, but they're willing to. So if we had, let's say, this circuit right here, let's circle all the actual loads. We see a bulb, right? We see a bulb, right? But there's one more. What is this thing? Yeah, so this would be like, this is like the dimmer, right? So, and it may even be a rheostat, but whatever. We have a load right here, and then we have, if this load is in the series part, right? That's the series part. Isn't it accurate to say we also have a load in this part and in this part? So that's the parallel part. So we have a load in the series part and a load in the parallel part. That's why it's a series parallel. Make sense? So if you were to look at some of these back here, way back, this was just parallel. There's a load here and a load here. There's no load up here. We have an amp meter here, but there's no load in the series part. This one here is the first time that we actually have a load in the series part, so that's why it's series parallel. Cool, so everybody should understand what a series parallel is. It's not a real big deal. But the way we apply some of those Ohm's law and whatnot is slightly different. But actually, it's just really combined. You got to know series and you got to know parallel. And if you know those two, very minimal to understand series parallel. So if we were to look at this, the total resistance gets a little weird because you basically have to calculate the parallel resistance. Remember with that R1, 1 over R1 plus 1 over R2, and etc. But you don't just throw the series part in. You actually have to understand it's the series standalone plus the total of the parallel. So we'd calculate the total for the parallel plus the series equals the total of the total circuit. Kind of makes sense? And then as for the current, it's really the same. So the current in the series part is going to be the total of the 2 parallel parts, or 3 or 4 or 5, however many lanes, right? So the total of the freeway is going to be the same as all the exits off the freeway, right? Now, when it comes to voltage, that's when it's going to be a little different. So here we go, measuring the voltage available. We got a 12-volt battery, so we got 12 volts coming off the battery, going to the fuse. We lose a little bit going through the fuse, so we end up with 11.9. We go through the switch, which is closed. We lose a little bit. We end up with 11.8. We go to our first load. Now, the load is designed to consume. How much? I don't know. We'd have to actually know the resistance of the load. But in this case, we've already got the math done for us just as a demonstration. It drops 4.7. So if we had 11.8 minus 4.7, we end up with 7.1. Should this be red or should this be green? Neither one, because it's what we call an intermediate voltage. We've dropped some of the voltage as designed, leaving 7.1 volts to both be dropped over the 2 bulbs. Each bulb gets 7.1, and each bulb drops approximately 7, leaving about 1/10 on the ground. So what's the purpose of this circuit? I mentioned this before. It's probably your interior dimmer. You turn the lights on, you got all your lights on inside. They're a little bit too bright while you're driving on the freeway at midnight and you're trying to get to wherever. So you go ahead and you turn that dimmer down. When you turn the dimmer down, that increases the resistance, which means it's going to consume more. So rather than 11.8, maybe instead, we get 11.8, we have 7.1 left over. If we turn the lights down, maybe we only have like maybe 4 volts left over. That's going to make these glow very dim. Make sense? Or if it's too dim and you can't see, you turn this up. That's going to lower the resistance, which means it's going to consume less, which means maybe you get 11 volts left over, and these are going to be more bright, right? So that's the only time you'd really see this circuit in practical application. I mean, they're not really all that hard to diagnose either. If you had an open dimmer, what would be the status of the bulbs? Both bulbs would be out. What if you had one bulb in op and one bulb work? Do you think it's the dimmer? Right, exactly. So like if this bulb is in op, we know that we need to do it from here to here, right? So it's kind of the same. It's not a real big deal. Essentially, it's identical to a regular parallel circuit. You're just going to break it down into a series and diagnose it. The only difference is you got to understand, by design, there is a load in the series part. Okay. All right. So if we were to do this on a vehicle, or on the board, let's just say I asked, what should the voltage be? All right, trick question, kind of. What should the voltage be right here as it's shown right now? 0. How come? Bingo. So let's redraw that. Because again, we don't normally test it with the switch open. We're not testing anything. So let's draw the switch closed. What should it be at this point now? Yeah, so let's make it easy. We'll do 12-ish, but you're right. It should probably be a little down. All right, and this potentiometer is in the series part, and it is a resistor. I don't know how much, but it's something. With that being said, what should be at point F?
Less than 12.
That's true, but how much? I don't know. You understand? You don't know because you don't know what the resistance is, but less than 12. Well, let's just say we did funny numbers, and let's just say the total resistance of these two was, let's make it 4 ohms. Not 4 and 4, but like if the total resistance, you remember how we did that long calculation of 1 over R plus 1 over R plus whatever. Let's just say that number came to 4. And let's just say this individual rheostat dimmer came to 4. They're the series part of the circuit is 4 ohms and the parallel part is 4 ohms. What should we have at point F? This is equal to these combined. It should be 6, and that's a little bit weird, right? Because if you have 4 ohms and 4 ohms, the first part is equally strong as the second part is combined. So the first part's going to consume half. Get what I'm saying? But to actually predict this, you'd have to know what the resistance is of everything, and you'd have to do a bit of math. And that's the one time you'd actually have to do that math that we talked about. But the good news for you, never on a customer car and definitely not part of your hands-on test. So today will be fun. You'll get to do some experiments. You get to do some math. You might come up with a number that's different than someone else's, and then I'm going to have to try to help you with some assistance of AI. Just because I'm so resistant to getting good at this every time I teach this, because it's, you know, it's only the only time I'll ever do these calculations is today. And the next time I teach electrical will probably be 2 or 3 years from now, and I'll do it one more day, right? So I'll get actually kind of good at the end of today, and then I'll purposely flush that information because I don't even want it, okay? So what should our measurement be at point J? That should be 0, right? So you guys got it. I mean, basically, the 12 volt side will be the same. The ground side will be the same. It's this intermediate right here, which I'm going to make blue so you understand. After the first resistor that's in the series part, there's going to be some amount of weird voltage right there, depending on how many ohms this thing is, right? So it's not a super big deal. The way we diagnose it's about the same. Cool. So I'm going to have you guys do some other more complicated experiments with some different switches and some whatnot. That one I'm not going to give you a rundown on that. We'll figure that one out. So a couple ways that we can apply Ohm's law, right? Because we're about to summarize this one. Let me just skip. Yeah, okay, got it. Later, not now. So, and all this really is, this is a switch that's just a little bit like a multifunction switch or a hazard switch or something. This, if you look at it, is really just a number of different switches. So like, if you follow this wire, it comes into this point. Is it connected to anything? No. So you'd know you'd have 12 volts coming in here, you'd have 0 volts on everything else. But what if I were to connect this to this? I'll give you just a little bit. If I were to connect this 12 volts through this switch, you know that you should have 12 going down to here and 12 going down to here. But what should you have here? There's no connection, right? So you're just looking at it as an individual circuit. If there's no connection to this, that should be 0 and 0 because there's no connection there. Cool? So what if I connect both? Well, then it would go 12 and 12. But what if I connect 0? That would be just 12 to right here, and then all the rest of this should be ground, right? So like, this is nothing more than multiple different switches that connect different parts of the circuit with one push of a button, because it's a more complex switch, that's all. Yeah. Yeah, that part's a little bit weird, but don't worry, we'll get there. All right, so summarizing, this was kind of long. This is like 4 full class sessions. So let's summarize why you need to know what we did. Ohm's law, like I told you, I really don't hate the math. It's just unproductive to me. So it's like you want me to do something, to calculate something, so that I can predict something, so that for what? I'm just going to measure it. I'm just going to measure it and fix the car, make the recommendation, bill the money, right? That's kind of where I'm at. But here's why it's helpful. If you can perform the math and predict and then verify the measurements, it shows you understand. And you have to understand. You can't be like, I don't like math, so I can't understand it. You don't really have to do a lot of math to understand it, but you have to at least be able to do some so you can prove. If resistance goes up, amperage goes down. If resistance doubles, the amperage will be half. If the voltage doubles, the amperage will be double. If the voltage is half, the amperage will be half, right? So there's that diagram I showed you with the ohm guy with the rope pulling up on it. You could basically know everything you need to know by just remembering that. Cool? You can calculate electrical quantities in a series circuit or parallel too, while cross-checking the actual measurements. So I wouldn't call this Ohm's law so much as you need to be able to look at a circuit and predict what should be where. And then after that, you should be able to measure it and be like, is this what it was supposed to have? And if you predict it correctly, usually through tracing, which is what we're going to do when we get back, you're going to trace circuits. And if you predict it correctly and you trace it correctly and then you measure it and it has what it's supposed to have, you can determine these things are good. But what about when you measure it and it has something different than what it was supposed to have? Something's bad, but what is bad, right? So that's more of where you need to know this. You need to be able to predict it and then understand, like, if it measured something it wasn't supposed to, what's that mean? Cool? And then additionally, and probably more practically, use the relationship that it demonstrates to guide you through the diagnosis process. So if you were to do a voltage drop and the voltage drop was more than it was supposed to be, right? Across the switch, we expect maybe 0.1, 0.2 would be the max. What if you dropped 6 volts across the switch? What's that tell you? Yeah, but be more specific than bad. Bingo. You know that because of Ohm's law. So if you have excessive voltage dropping across the switch, you know it has excessive internal resistance. You already know kind of what you got. Like, yes, the switch is bad. I agree. But specifically, how I'd write that up more legally is excessive voltage drop, which is associated with this excessive resistance. If you want to double check yourself, go ahead and measure the resistance. But sometimes your resistance measurement with your little meter and your little 9-volt battery, it might not show that much resistance, but when you put a lot of amps through the circuit, you can measure the resistance more effectively through a voltage calculation. Cool, so that's good. And then understand, you know this relationship. Amperage can't exist without both voltage and resistance. So resistance is kind of a weird way to put it. Continuity, I think, would be a better word here. You could have voltage, but if you have no continuity to the load, there's going to be no flow. The load's not going to work. I think you would know that. What if the amperage is too low? That would mean one of two things. If the amp getting pushed through the tunnel is too low, it's either A, the voltage is too low, which is possible because, you know, batteries can go dead, right? But if we verify that the battery voltage is good, from there, if the amperage is too low, the lights are too dim, the motor's too slow, etc., it's probably because of excessive resistance. The resistance would be too high. Then we're looking for things like corroded wires, loose-fitting terminals, etc. Maybe the brushes in the motor are not contacting the inner parts in the commutator, and that's why the motor is not working right. Right? So we would track down the excessive resistance. And after spring break and your practical, we get into wiring diagrams. Just understand the wiring diagram colors don't necessarily tell you what the voltage should be, so you need to be able to trace it, like we've been starting to. You need to be able to trace it so you can predict what it should be. And test lights we used a little. I'm good with a test light. Like right there you would say that fuse is receiving power, right? But what's the voltage there? I don't know. So a test light's good as like a quick tool. Is this fuse getting power? Yes. On the other side, the fuse is getting power? Yes. Therefore, the fuse is good. But anything that a test light can do, a meter can do better and more thorough. But a test light can be a quick tool. So I'm okay with it. Just understand, this test light doesn't have a whole lot of resistance. So if you're testing computerized stuff, you're giving it an alternative path to ground that doesn't have a lot of resistance. Low resistance means high amps, right? Computers do not like high amps. So the test light's good, but not preferred for computerized circuits, FYI. Okay, and then, just make sure we know approximately the voltage range so that we're using the right type of stuff. Definitely don't use it on SRS, and like I mentioned about the computer. So if it's with airbags, no. Although it'd be fun. Cool, so just summarizing, test light, clip it to ground, poke the stuff, poke another thing. So this is just basically an available voltage tester, but it doesn't give you a number, it gives you a brightness. So if you had excessive voltage drop across the switch, how would that look? Well, with your meter, you'd have 12 volts coming in and 6 volts going out. On a test light, you'd have a bright bulb beginning, going into the switch, and coming out of the switch, what would you have? Dim bulb. So it's kind of the same idea, but it's just not specific. So like, what's dim mean? I don't know. I like the numbers. Numbers are a little better for today's day and era, potentially in court and whatnot. Right? Now, fuse jumper we didn't talk a ton about, but let's just say you've got these little alligator clips. They go on a wire which goes through a fuse jumper, which goes to another alligator clip. What would we do with these? Let's just say if I were to jump way back to this diagram, and let's say that we thought that this switch was no good, what if I took a fuse jumper and I tied it into C, and then I jumped it over to D? What am I doing with that fuse jumper?
Making a complete circuit, if it's open and it doesn't work and the switch doesn't.
The word I like is like a bypass. If I bypass the switch and it fixes it, it was because the switch wasn't working. Right? So fuse jumper leads are legit. But if I bypassed this to this, with a fuse jumper, there's no resistance. I'm going to have way excessive amperage. I'm going to blow the fuse. So fuse jumper is good, but you can't fuse jumper across a load. If I thought that this wire right here was bad, I could tie into H and I could jump to ground. And if it resolved the issue, that tells me that this wire right here is bad, but just don't jump it across the load, because then you've taken the resistance out of the circuit and now it has very low resistance, which means the amperage is going to be very, very high. That's the guy pulling on the rope. He just lets go of the rope. There's going to be a lot of amps flowing through, and you're probably going to blow the fuse, or that's why the fuse jumper is a fuse jumper, not just a jumper, which we could call like a little fire starter, which would be fun. Cool. So that's a legitimate test. We did a little bit of jumpers when we tested relays, right? Now, when we talk about open shorts, bad grounds, high resistance, we can't exactly summarize that, but we've talked about this extensively and applied it in many different ways. So if you've understood this and we move on to the car and the vehicle has an electrical problem, it will pretty much be an open, a short, a bad ground, or even just in generally a bad connection, and a high resistance, right? That's like pretty much what we're hunting. So if the car came in with the taillight bulb was dim, I would suspect that's going to be a high resistance. Cool. So I already know my story is going to say high resistance. Where is it though? I don't know. I got to test it. If the car came in with let's say the brake lights were not working, neither one of them not working, I suspect will most likely be an open, right? An open means it's totally an op. A high resistance, which means it'd be dim or slow or something. But if it had an open, in my story, I'd be saying I tested this. I found a 12 volt drop going across this such and such wire, determining it's an open, right? It's not a high resistance, it's an open, which means it's totally cut, chewed, broken, something like that. When we say a bad ground, that really implies it's a ground with excessive resistance, which most likely looks like corrosion, loose bolt, something that's not having a good connection to the chassis. So if we say bad ground, that's the one thing we kind of like give a little leniency on. Like a fuse, for example. If I say a bad fuse, what's that mean? Was it misbehaving? Like, it's probably a blown fuse. That would mean it's an open fuse. An open fuse even better. When we say bad grounds, it's like, that really just means high resistance across the ground. So I'll let you get away with bad for that one. Other times I'm probably going to say bad, that's going to be a no. Or then, you know, high resistance and stuff, that can be anywhere. What about a short? Remember the short? Short circuit means the electrons are not going the full length of the circuit. If the short is occurring before the load, that will most likely, you know, electrons path of least resistance, they're not going to go through the load, they're going to go through the short. If the short's before the load, that means there's no resistance. It's like 0.2 ohms. 12 volts divided by 0.2 ohms is like a lot of amps. So what do you think is going to happen if it's a short before the load? Probably going to, true, and what's it going to do? It's probably going to blow the fuse. And then you put a new fuse, it blows that fuse, right? So we'd have to troubleshoot the short, and that was the thing that we covered last time, was like you can use the bulb and you can disconnect things till the bulb goes out, and that shows you've taken away the short to ground.
What's the difference between the short and the bypass, though?
It's I think an image would be the best way. It essentially,
I know short's not good.
they could be kind of the same. So if I pick a short, which I know there's one right back here. All right, this is a short. It bypassed the load, but in a weird way. It went directly from the positive directly to ground. Cool. I would consider them both to be shorts, but if it was a bypass, maybe it shorted from here to here. It's not shorted to ground, but it bypassed the load, right? So that means we just lowered the resistance. If we lower the resistance, the amperage is going to go up, blow the fuse. Cool? Whereas if, for example, we have in, let's say, none of these are amazing, but let's say that I redraw this. Let's say that I had a short, let me pick one. See, none of these are actually going to work for exactly what I wanted to show. Let me see if I can pick one. I wanted to find a ground-controlled circuit just to illustrate exactly what I'm trying to tell you. Okay, nice. What if, well, that's a short right there. So if you notice, I made a short, I'll even redraw it. If we make a short from here to ground, do you think that's going to blow the fuse? Because look, the electrons still have to go through the same bulbs. What is it bypassing in its short? The switch. So what's going to happen in this circuit if it's shorted to ground at that point? What happens when I open the switch? It doesn't make any difference. It's got 12 volts all the time, and it's shorted to ground, so that means I open or close the switch, it makes no difference. They're turned on all the time, right? So a short doesn't necessarily mean the fuse is blown. A short just means the circuit's not going to be functioning as designed, right? So I just gave you that example of what a short could be. How would we determine it? Well, if all these bulbs were illuminated, let's draw them illuminated, glowing. Let's do this, this, this. If these bulbs are all glowing, what could I do? Maybe I disconnect. How about if I disconnect right here and it makes no difference, that means the short must be before it. If I disconnected here and it made it go out, that would mean the switch must be stuck closed. I would sell a switch. But if I disconnected here and it made no difference, that means the short must be somewhere before here. If I disconnected here and it made no difference, it must be before. If I disconnected here and it made no difference, it must be before. But what if I disconnected at H and all of a sudden all these lights went out? That would mean that this wire must be shorted to ground. Makes sense? So we would just disconnect things until the lights go out, and that tells us we've taken away the source of the short by disconnecting it. Cool, so that's how we would apply it. And that's true, by the way, for series, for parallel, and everything. If it was applied on a series circuit, you know, you would go about it just picturing what would cause that thing to stay shorted. If it was on a parallel part, you could probably already determine where the short isn't, so you could disconnect less stuff, less things. Right, we're pretty close.
Is that like tracing?
Sort.
Or no?
Yes, how we just traced it. You know how I highlight it? If I highlight it red and I highlight it green, we're just tracing the circuit. We're visualizing how the electrons flow. We're color coding it so it's easy for us to test and know what our measurements should be. Yeah. Cool. And then here's an example of like a real world find, right? So if you test with your meter, I've got excessive resistance and it's indicated by excessive voltage drop, or you actually test it with ohms, then you're looking for something like this. This looks like high resistance. It looks to me like this was laying on an exhaust and it got burned. And then that ruined the insulation, and then it got corroded, which added resistance, right? Or if this one, you see, you could barely tell, but that one's kind of green, that one's corroded. Or if a wire is completely cut, that would be an open, right? So if you test for a high resistance, probably looking for corrosion, loose connections. If you test for an open, the wire's probably actually literally broken in half. You can find both. Cool. Oh, and some other cool things you can do depending on what meter you have. They do have meters that'll beep when there's an open or when there's a good continuity or whatever. So use some of the features to help you find it. If you know there's an open and you put it on the continuity test with the little beeper and you're wiggling and moving and all of a sudden you wiggle and it goes beep, you'll be like, oh, it's there. That's when you can cut into it and hopefully find this. You don't want to just start cutting everything. You're going to make a mess, right? And this is a little crazy. I've seen people use a compass. They'll actually move the compass along the wire, and when there's an open, the compass will move. It changes the electromagnetic field. Current flow generates an electromagnetic field. The electromagnetic field has an effect on the compass, and then if there's an open, it will actually change. It's kind of weird. By that same technology, they do have specialized short circuit detection and open detections and that type of stuff. I know a lot of people, we don't really use this because it may be used on like trailers or something where it's more accessible, but if you're trying to use some of these specialized equipment, it kind of covers for you not really knowing what you're doing that well, but also in a car, a lot of the wiring is hard to access. It's behind panels. These specialized short testers and open testers, you need to be like almost right on the wire. So you'd have to pull a lot of interior panels off and then run it across the wire. I would rather pull one interior panel off, make a measurement, skip a bunch, pull another one, make a measurement, and determine which panels I have to take off. I don't just strip the car. So not particularly helpful for automotive, but maybe trailers or something like that. Cool. High resistance, you guys remember. Unintended resistance, corroded. Maybe incorrectly sized cable, but you know what's kind of common is, I yelled at some students the other day, not you guys, other ones. When we go to test on the car, right at the end of the semester, when we cover our lighting systems, back probing is critical. Back probing is where we slip this in to, you know, a connector like if it's like this, we back probe it. We go in from this way and we just barely make a connection. Nothing's harmed. Cool? And we can get a measurement there. What it's not is disconnect it and ram this sucker in there because you had a terminal that was this big and now the terminal's this big. You just made high resistance with your testing methods.
Why is back probing better than doing it from the front?
I'll bite on that, but when we do harnesses, I think you'll understand. I was looking to see if I had any good connectors for that demonstration. Let me take a look at this. All right, this would kind of do it. On this, there's a spring-loaded terminal, right? When I go in here, I'm forcing the terminal open, right? If this is too big, I've basically taken that terminal and said like, ha-ha, cool. Whereas if you back probe it, we're not forcing anything open. We're just simply like, typically on a wire, there's a terminal, like a little seal. We're not spreading anything open. We're just making a little contact. We're not.
So it's not interrupting, it's already there.
Exactly. We're just touching something that's crimped. So like on the back side, it's crimped to the wire. We're just making a contact with the metal. On the front side, you could technically, there's actually, truthfully, there's nothing wrong with front probing if you just lightly touch it. But who's going to hold it there? So if you're going to hold it there, you got to hold it there, but you got to be in 2 places at once. So normally techs are like, send it. See, it'll hold itself as long as I ram it in there. Whereas with the back probe, it typically has, you know, the plastic part of the connector. You can kind of prop it up against the connector, just barely make a connection, less harmful. So when we talk about terminals and pin fit, I've seen cars bought back, lemon lawed, all sorts of stuff because, you know, the technician went in, or sometimes even just from the factory, a terminal's not correctly maintained or produced or whatever. A loose terminal will give you, yes, it's connected, now it's not, it is, it isn't. Like if it was a bulb, can't you imagine the bulb flicker? What if it's a terminal that powers up a computer? Your computer's online, it's offline. It's online, it's offline. You're driving the car and it's freaking out. It's shutting down, it's waking up, it's losing, like, it can cause some messed up stuff.
It's more of a thing for cars that have like the typical plastic connectors and stuff.
Yes.
Only reason I ask is when I ran the wiring harness on a 70 bug, it was
Okay.
just crude and it was just like all spatula and connected.
Yeah, but that's like a vintage, whatever. I can't even remember a couple of those brands. That's fine. But on a new car, because there has to be so many more wires with so many more sensors, the terminals are tiny and they're very sensitive. And if you even slightly are rough with them, you're done. So on those old ones, painless wiring or something, they're much more beefy. Because I'd love for them to be beefy on a new car, but then your connectors can be huge. So we need to make them tiny, sadly. Cool. I think overall you guys are pretty good. So if you have no questions, you've successfully completed all the theories of electrical. And